Yeah, everybody. My name's Alex. I'm a postdoc at Intuitive Machines, which is where the Lunar Reconnaissance Orbiter Camera and Shadow Cam Science Operations Centers live now. That's what I do most of my work with. And this work here, we used Shadow Cam data to compare the depth diameter using garden regolith in all geologic terrains on the moon. And we know from work looking at temporal imaging over the lifetime of the LROC mission that their production rates, the observed production rates of small craters exceed what models predict. So they're really important for understanding how regolith is produced in different terrains and how the surface of the moon is modified over time. So, I'll show this example while we're here, actually. So this is one of the temporal imaging findings from Spire et al. 2016, where this is the before image and here's the after. And then on the right is a ratio of the after to before. So increased brightness pixels, bright pixels are an increase in brightness in that area, and dark pixels are a decrease. So I'm trying to show, sorry, I lost my so it's not just the crater itself that modifies the surface. There's this whole spread of distal and proximal reflectance zones that both increase and decrease the local reflectance and modifies the regolith. Okay, so primarily what we were looking at is the depth to diameter ratio, which decreases over time as a crater ages from infilling and degradation and widening of the rim by processes like bombardment by primaries, but also secondaries, sandblasting, seismic shaking. And the canonical number for the initial depth to diameter of a crater in that what we're looking at is 60 to 250 meter range. It's about 0.2, but we know from Hoover et al. 2024 that it's not a perfect number. They took 10 unambiguously fresh craters and looked at their depth diameters. It's more of a distribution. So one thing that we did is to try to maximize the number of craters per geologic unit that we got to try to increase the robustness of the statistical analyses. And then another number that's important for this work is 0.04, which has been put out in the literature as the point where a crater becomes too shallow to be identified in images. And on the right here, there's a model from Fassett and Thompson showing that the process of depth diameter decreasing over time is diameter dependent. So for the same interval of time, a 300-meter crater will see significantly more change to its depth to diameter ratio than a 1 kilometer crater. And looking at distributions of depth diameter across geologic units can allow us to make inferences about the target properties of those units. So for example, this work by Mahanti et al. In 2018 compared the depth diameter ratios of the distributions of the craters at the Apollo 16 and 17 planes. And you can see in the highlands where you'd expect the craters to be older than craters in the Mare, the distribution actually showed that there were larger depth diameter ratios in the highlands, consistent with fresher or younger craters than in the Mare, which is still an open question. We don't really know exactly why they found that difference, but they chalk it up to target properties. So that's something worth considering. And a few other previous works have looked into the question specifically of whether depth diameter is significant in polar or permanently shadowed regions on the moon versus equatorial regions. And some have found that across varying diameter ranges, they did find the depth diameter ratio to be shallower in general in polar regions as well. Sorry, these were both in polar regions. But then one study looking at the Shoemaker PSR using 150 meter to 400 meter craters concluded that there was no difference in the craters looked at. So this was the question we were trying to address, and we wanted to use shadow cam data to do that. And some of the papers, for example, this is a cartoon by Rubenenko et al., hypothesized that ice or volatile enrichment in the regolith may be responsible for that difference in depth diameter. So this is kind of the basic idea behind how shadow cam works. Because we're at the lunar poles and the moon's axial tilt is much smaller than the Earth's, only about 1.5 degrees. We don't get huge differences in seasonal lighting intervals. But there are some small differences, and this matters for shadow cam because often when we get high topographic highs, such as a crater rim here near the pole that's illuminated, it will reflect and scatter secondary illumination into the crater interior. And shadow cam was specifically designed to take advantage of these low levels of illumination. And so we can take images with shadow cam and build nice mosaics, such as this here in the top right, which is Shackleton crater right on the South Pole. And then an additional step of processing we've been able to do is to make digital terrain models by using stereo observations with shadow cam. So we take overlapping observations of area from different viewing angles, and then we can use the parallax between those to reconstruct the terrain, which is great. This wasn't part of the shadow cam proposal, but the Korean space agency has been to work that into our operations, which has been awesome. So the first 3 DTMs we were able to produce by this method were shadow cam and Faustini on the near side, and they're sort of typical large crater PSRs, circular, and then Sverdrup as a sort of an outlier on the far side, and also it's sort of an odd shape because Sverdrup crater forms this interesting complex with Henson here. So we looked at the 3 of those, we mapped craters across the floors, and so we've got the resolutions here. Yeah, so the mapping was done manually, where we just looked at the orthomosaics. So the mosaics have been orthorectified to the terrain model, and then just put fit circles to the crater rims. But we also used a slope overlay so that we could see the 0 slope point on the crater rim to see kind of exactly we think the rim is. So these are just images showing what those map shape files look like. And then we also considered that local slopes can have effects on the depth and diameter and other morphometry of the crater. And so we ignored craters that were on local slopes of greater than 5 degrees. And the way that we did that, this is actually an old figure, but what we did is we took the local terrain out to 3 crater radii. And what we're doing now, it's not shown here, but we're actually just taking an annulus of that terrain that excludes the crater in the center of that subsection of the terrain model. We fit a plane to that annulus, like you see here, and then we subtract that. So it's just a first order correction that levels off the local terrain and finds the local slope angle, so that we can decide whether or not to measure it. And you can see that the effect is pretty subtle. So for this crater here, you have this gradient going from top left to bottom right, and after accounting for the local slope, it's evened out into a little bit more of a flat area. And then I saw a couple of abstracts on the schedule for tomorrow talking about very similar methods to these. So that's awesome. I'm excited to kind of hear how everybody's been doing this part. But so what we're doing is using radial profiles, and we draw radial profiles out from the center of the circle and find the peak position along the profile, which is determined as a point where the slope changes from positive to negative in the outward direction. And then we take we fit a circle to the horizontal positions of those peaks. To get the diameter of the crater, we just use the diameter of that circle. And then the depth is calculated as the median elevation of those peak points we identified, minus pick the lowest elevation pixel. And mainly the reasons we're doing those is because of the work that we're trying to compare to that I'll get to here, but I've mentioned the Vasilevsky and Lee paper that determined that Shoemaker didn't really look like the craters were shallower. So there's I'll come back to that, but and by the way, this one was we intentionally offset the initial position of the rim just to show how the code operates. Okay, so this is kind of the main result here. So we're looking at curves fit to the normalized distributions of depth to diameter. So on the horizontal axis, we have increasing depth to diameter from left to right. So over here, that sort of 0.2 number that's used to suggest that a crater might be extremely fresh. And then down here, 0.04, which is kind of talked about as being the point where a crater is no longer detectable. The Apollo sites are in these filled curves, and then the ESR craters that we measured are just under these dashed curves. And you can see that the peaks of these curves are quite a bit different. And I'll break that down a little bit.
Can I ask a quick question?
Please, yeah.
On the previous, that one. So at the Apollo sites, were those just measured from images or were those measured from DTMs?
From DTMs. Yeah, same procedure for both sides. And they, I'll just mention that the NAC DTMs of the Apollo sites are higher resolution shadow DTMs, but that's why we excluded diameters below 60 meters. So, but we did look at the diameter. This is actually kind of interesting. I think we looked at the depth diameters of the craters below 60 meters in the Apollo sites. And this is kind of where it matters. Most of them sit in kind of this upper area here, whereas the first point here in the PSRs, the small craters are not sitting here. So this is kind of a lot that's applied. We actually got a suggestion from a reviewer this morning that this needs to be broken down. So I'm excited to do that, but didn't have time on the drive up today. But yeah, so what we're looking at is depth on the vertical axis and diameter on the horizontal axis. These dashed lines represent a constant, it's log. So we're looking at a constant depth to diameter value. These dashed lines, which are labeled here. So this is like, below this is where a crater should disappear, and above it is where it spends most of its lifetime. And then in this upper region here would be where you should find fresh craters. So some of the differences, and then these sort of faint, smaller markers are the Apollo sites, and then the larger, bolder markers are the PSR craters. So the first difference that we noticed here is the percentage of craters in that fresh or deep regime where you'd expect to find fresh craters, and the fraction of each geologic terrain that has small craters in those ranges is pretty different. Only about 1.5% in PSRs versus more than 15%. The Apollo sites, and then looking here, down here where this is thought to be kind of where craters become undetectable, we see there are quite a few, more than 40% of the small craters in PSRs that we looked at sit in that range versus only about 15% of the Apollo craters. And then another interesting point is when we look at diameter bins, if we look at the shallowest diameter bin, this is showing 60 to 100 meter diameters. The mean depth to diameter in the PSR craters was about 10% below the mean for the whole group, whereas in the Apollos, this is what I was getting to before, about 15% greater than. So you'd expect to find a lot of small, fresh craters with large depth to diameter values, but we don't see that in the PSR areas, the same Apollo sites. Okay, this is just another way of looking at those distributions, but we're looking at on the left, a cumulative distribution function. So you can see the comparison of the Apollo sites versus the PSR sites. I think the main thing I want to point out here is they're shallower overall, but also they form initially shallower, which kind of goes with what I was saying about that. The very small craters that don't have the large depth of diameter that we expect. And then they're shallower over their lifetimes. We don't see the cumulative distribution functions catch up at some point, like at 0.06 or something. Then most of the distribution sits there. And then on the right, this is, I don't know if I totally agree with this method, but this has been established in some of the papers we want to compare to. So basically all they're doing is taking the slope of the cumulative distribution function. So the change in frequency of craters of certain depth diameters, cross diameter, and scaling it by the rate of production of craters of those diameters that we expect to see. And so according to this method, gives a degradation rate on the vertical axis versus depth diameter on the horizontal axis. So what we're seeing is after a crater has sort of gone through that very fresh initial stage of its life, and then is into the 0.1 down to 0.06 sort of intermediate range, what we're seeing is that the degradation rates, what we're inferring from this plot anyway, is that the degradation rates are higher in the PSR areas that we looked at than they are in the Apollo sites. And then, what do these shallow craters actually look like if they exist below 0.04? They just look like craters. They look like old degraded craters, but they're there and they're visible in both the images and in the terrain models, and they're present across all of the whole diameter range that we examined. So it's not just small craters in particular. There are a few towards that upper diameter range where we also see them. So one of the questions we kept asking is, we're looking at these craters under secondary illumination, scattered light from the crater, the host crater rim of that PSR. So maybe this is an effect of illumination where that scattered light makes really, really shallow depressions more visible, and maybe these shallow craters exist everywhere, and it's just a function of illumination, which is kind of the opposite of what I would expect, but we wanted to look at it anyway. So we used the PSR equatorial analog Lorman crater. So this is really close to the equator of the moon, and took overlapping images with both LROC and shadow cam. So these are kind of the approximations of what the lighting looked like. So shadow cam, we used the illuminated rim providing secondary illumination, and then for the LROC image, we took that when the sun was just over the horizon, crater wall there. So the incidence angles are very close between the LROC and shadow cam observations. And this is just blinking back and forth between two co-registered images on that site. And we went through and counted these craters, and there's no difference in the number of craters that we see, and not especially in the diameter range that we're looking at, 60 to 200. So we don't think this is an effective illumination. And then just getting back to the point I mentioned about Vasilevsky and Lee 2024, they concluded that the craters they looked at in the Shoemaker PSR didn't appear to have any difference in depth of diameter. But there are a couple of key differences between what we were doing and what they were doing. So their method of determining depth of diameter, they put a circle around the crater, take the maximum elevation pixel and the minimum elevation pixel, and Stuart's shaking his head. He's got a beautiful paper on why not to do that, and I don't think they read it. That's all right. And then they also were looking at a diameter range of 150 to 400 meters. So what we did is we took their method and modified our code to use the same method. And then and they were also using the LOLA data, the LOLA LDBM. So we took our code to use their method. We don't know exactly which craters they used. It's not in the paper. It's not available online. But there is a figure that shows a subsection of them. So we found where those craters were, mapped the same craters, and then just ran the analysis on the shadow cam DTM and the LDEM craters using their method. And what we find is that they're really well correlated across that diameter range of 150 to 400 meters. The R square here was like 0.89. So what we're concluding from that is that it's a consequence of the diameter range that they looked at. So it's really the shallowest craters where the difference is most significant in the range we looked at. And also probably there's a consequence of the method that they were using max pixel minus min pixel. Okay, and then I don't think I pointed this out, I apologize, but when we're looking at the inferred degradation rate, probably go back. Just gonna flip that really quick. There's okay. Yeah, so I don't think I pointed this out, but Faustini and Shoemaker, their degradation rates are sort of up here and kind of together, and then Sverdrup is sort of intermediate. And there are a couple of other interesting differences about the craters in the Sverdrup PSR that we looked at. For one thing, in the 0.06 to 0.1 diameter range, that kind of intermediate lifetime, or not so super shallow yet. They have a lot more craters in that range at larger diameters. So in the 150 to 250 meter bin that we looked at, Sverdrup starts to look a lot more like the Apollo sites. And then, as I mentioned, there's that potentially intermediate degradation rate. So we wanted to know what the reason for this is, and what we think is that, as I mentioned, it's different from Faustini and Shoemaker. One, because it's on the far side, but we don't really know why that would create a difference. But something that's more significant and came out recently. I should have a citation here, but it's really recent. But looking at the ages of cold trapping areas inside those PSRs. So this is our incident all 2026. It just came out in Nature a few weeks or months ago. This year's going by. But so basically what they showed is that based on the polar wander of the moon, the ages of cold trapping areas are not the same all across different PSRs. And in particular, Faustini and Shoemaker being those sort of ideal circular PSRs, the vast majority of those cold trapping areas have existed from 3 billion years or earlier. Whereas in Sverdrup, it's a homogeneous cold trapping area in terms of age, where it's only come gradually from the where the wall meets the floor to where it is now. And that's some of those areas are less than 2, maybe even less than 1 billion years. And then another important data point there is that there are areas on the Sverdrup floor with annual maximum temperatures above 120 Kelvin, whereas in Faustini and Shoemaker, you won't find any over 110, maybe even 105, depending on which model you're. And that's important because the number that's used as the ice stability temperature in PSRs is 110 Kelvin. So the thermal environment in Sverdrup is probably different, and the age of the cold trapping area is probably different. So it may be that the accumulation of volatiles over the history of Sverdrup crater has maybe favored recent deposition on the surface as opposed to subsurface deposits, and that would lead us to if the difference in depth and diameter is due to volatile enrichment in the subsurface, that would put Sverdrup at an intermediate point between the other two, because those volatiles have not been deposited as the others. So the kind of wrapping up the whole thing here, looking at the way that the depth to diameter is distributed across those craters inside the PSRs, they appear to form shallow initially. They may degrade more rapidly, and the fact that we can see many of them at depth to diameters well below 0.04 might also indicate that they persist in heavily degraded states for longer. We really don't know exactly why that is. So looking at craters with diameters smaller than 100 meters, They're in particular more significantly shallower than their counterparts. So that would probably be consistent with unique properties in the upper few meters, maybe 10 meters at most of PSR regulation. Again, we don't know, maybe it's volatile enrichment, porosity in the PSR regolith could have a significant effect on the physics of crater formation, or maybe regolith cohesion or something. Another comment from one of our reviewers was that there's probably a lot of good literature about impact into place for volatile enriched targets. And that's something we want to make sure we look into. And I think maybe we to talk about that today, but I'll find out who you are and talk to you. So yeah, spur might be different. We don't know, but overall, it does seem to be an important property of the small craters and PSRs, and so future missions wanting to look for volatiles and not have their reverse slide into the crater should come up. That should be. Thanks.
All right, we definitely got some time for questions. Margaret starts.
Did you go back to your crater degradation rate that was unitless and explain a little bit more how you derived that? Is it related to any sort of landscape diffusion models?
No, it's much simpler than you'd think. It's just taking Neugier's production function, which at this range, 60 to 250 meters is just a constant. And then taking the slope of the CDFs here. And so it just I should put the equation here because it's a good question. But yeah, it's in a couple of papers and then our paper and abstracts. But yeah, it's not a very complicated stuff.
Okay, so a comment and perhaps a word of warning. We got murdered trying to do the PSRs on series because they look like they're all landslide deposits and are in a series published GTM wasn't good enough to tell exactly what was happening. But we were seeing really the effects of landslides being the major like geomorphological driver of PSR craters on series. Moon is not series though. One thing to think about is that what makes really good PSRs is also having really steep slopes, so you don't have a lot of that secondary illumination. That's also the best place for landscape diffusion to move the most mass the quickest. So I think it might be prudent to run a quick landscape evolution model just to see if that could be a competing hypothesis. I definitely agree something is filling in these craters. But my hunch is that junk from the crater walls is much easier to source than volatiles at this point in lunar history. So I think it would be a really interesting analysis to really bolster your volatiles hypothesis or maybe present an alternative. So really nice work, but I wanted to jump in there going, oh no, be careful at PSRs because what makes them the best PSR also makes them the worst place to preserve topography.
Yeah, okay, thanks. Yeah, that is something we're keeping an eye on the shadow cam too, especially is looking for any sign of temporal changes on especially the steep wall slopes. Diffusion and so far nothing too significant, but definitely.
And it may not be that the landscape evolution rate has to be that fast because like the South Florida topography is 3 and some change billion years old. You don't need a whole lot of pebbles rolling down the hill over 3 billion years to do some stuff. So very cool work.
Thank you.
So I was also going to ask a question about this slide for on the left. I'm curious to hear first what your take is on the fact that the shape of those curves, that the Apollo 17 curve shape is so much more like the South Polar ones than it is like the Apollo 16 one. You thought about that at all?
I haven't thought too much about it. Yeah, it is interesting. That was kind of the main finding of the Monty et al. 2018 paper that looked at those. Was that it was like super unexpected to see that.
So my follow-up question to that then is when you gathered craters from the Apollo 17 area, did you do any sorting out? There's lots of little like Tycho secondary chains there. It's right on the Tycho Ray, and like from looking at that area around the Taurus Littrow Valley, there's lots of small secondary craters there. So I'm just wondering if that could also be an effect if you didn't filter any of those out when you started, if you're also seeing a difference between primary and secondary crater diameter ratios.
No, that there was no filtering like
Okay.
that. I didn't collect those data, but as
Okay.
far as I know, there was no filtering like that done. The one, the one kind of, the analysis they did that I was really expecting to show something was that they looked at depth to diameter versus distance from the Lincoln scarf at 17, and they found no correlation. And I just thought that maybe some seismic shaking near the scarf has something to do with it, making the craters in the Moria look shallower, but there was no correlation there, so it's still kind of an option. But I like the point about the Tycho sectaries. It's something I will come back and look at. Thank you.
I think we're technically past time, but it's discussion next anyway, so I'm just gonna keep us rolling. So Jamie, I think you had a question.
Well, I'm not clear how the plot on the left tells why small craters and PSRs are shallower over their lifetimes. Tell me how you draw that conclusion.
Because, well, it's under the assumption that crater production is more or less the same everywhere on the Earth, with some uncertainty. And so even though it looks like they form shallower just because of the difference in the position of the freshest craters here on the plot, the curves should converge at some point over the lifetime because the processes that are degrading them are the same.
But those are Kuhn curves. So why don't we just compare them statistically to find out which ones are significantly different, which are not? I don't see how you can draw anything from just a plot like that. I'm assuming that's what you're doing, but maybe I'm not.
Could you elaborate on what you mean by, like, what statistics is it?
Well, what in that plot tells you that those are shallower?
The horizontal axis is the depth of the diameters.
Okay, but what are the error bars on that?
Well, I don't have the error bars plotted anywhere, but we have error statistics calculated for every measurement. And so, like, for example, this one here, the error is 0.0. This is the one sigma is 0.007. So that would change, and we don't go out to 3 decimal places on
No,
our
okay,
actual.
but I still don't see why you wouldn't just do a test and not try to draw conclusions from a picture that when you can do it numerically.
Yeah, which conclusion specifically are you asking? Because we may have done that.
Well, look, okay, so you look at those cube curves.
Mhm.
Are they drawn from the same population?
Oh, do you mean like a KS?
That's one way to do it.
Yeah, we did do a KS. And
Okay.
the values were like insanely.
So what's sample size, do you know?
For these curves in particular, yeah, each one is several hundred craters in the PSRs, and then the Apollo curves are like over 1,000 craters each.
Okay. But you didn't get any significant difference between any two when you did the KS test?
I'm not sure I know what you mean, but
Well, what test did you do again?
KS,
Yeah,
yeah.
so a KS test is designed to determine whether or not two Kuhn curves come from the same population. So if you do a pairwise comparison, you would think that with that size of the sample, that the ones on the right, the plots on the right would be, I mean, on the right of the left-hand plot.
The Apollo ones.
Yeah.
Oh, yeah, thank you. Which shows significantly different from the others. And that would give you something more than just a plot to indicate a clear difference of some sort. See what I'm getting at?
Yeah. We can include those statistics too.
Right, I mean, just looking at a picture doesn't tell me anything because it doesn't say anything about what went into it. So I would suggest that, but maybe your community doesn't
Okay,
get
no,
that rigorous, I don't know.
yeah, I'd be happy. There are other statistics in the paper too that I did not include in.
Can't hear you.
There are other statistics in the manuscript that
Oh.
I didn't include in the slides just for
Okay.
time, so. Yeah, I appreciate that feedback. We don't rely too heavily on these plots in particular we don't rely too heavily on these particular plots in the manuscript for the conclusions. I just wanted to have something visual rather than a large table.
Well, that's what we need to. Thank you.